Okay, so this is a direct current RL circuit, not to be confused with an alternating current circuit. So the formula that we have here is that the voltage drop across the inductor at any given time can be given by this exponential formula. Okay. Now for part A, it's a one-time constant, so T equals tau. Therefore, the voltage drop across the inductor is equal to the max voltage drop, which is 12, times e to the minus tau over tau, which is 12 times e to the minus 1. That's 4.4 volts. At what time is the current equal to 85% of its max? Okay, well, our formula for the current is that it's the max current is the EMF divided by the resistance, and then we use 1 minus e to the minus t over tau, right? Because at t equals 0, we want this term to be 1 so that the entire term is 0. Because at t equals 0, there's no current, because the inductor is blocking everything. Okay, so that's what we use for current. Now tau, L over R, let's see, L is 0.012 henries, and the resistance is 3, so this is 0.004 seconds. Okay, so I want my current to be 85% of the max current, so I'm going to put 0.85 times the EMF over R is equal to the EMF over R times this term. And then the EMF over R goes away. So now solving this, I get negative 0.15 is 1 minus e to the minus t over tau. And then rearranging things, wait a minute, I went ahead to myself. I took the 1 over. So I did a couple of steps here, sorry about that. I took this 1 and I moved it over to the other side. Alright, so now I'm making both of these positive and taking the natural log. I get t is equal to negative 0.004 times the natural log of 0.15. So that's 0.0076 seconds. Okay, so that's about 2 time constants in. We're about 85% of the way to max current, so that sounds right. For part C, at this moment, what's the voltage drop across the inductor? Well, there are a lot of ways to get that. I guess I could say that the voltage drop across the inductor is, I could just go straight like this and say it's 12 times e to the minus 0.0076 over 0.004, which is 1.8 volts. Or I could take advantage of the loop rule and I could say, well, the voltage drop across the resistor at this point is IR, and that's 85% of the maximum current times the resistance, or 85% of the EMF. And when 85% of 12 is 10.2 volts, right? And then the loop rule tells us that the EMF is equal to the voltage drop across the inductor plus the voltage drop across the resistor. We know that's 12, we know that's 1.8, we know that's 10.2, right? This also solves part D for us. We found the voltage drop across the inductor, and we found the voltage drop across the resistor. They're consistent with the loop rule. So either way you go, that seems to work.